So I was trying to read this article yesterday on a Japanese cooking site.
Oh.
And obviously, I don't read Japanese. So I did what we all do. I just right-click, hit translate, and boom. Kept reading, didn't even really think about it. It's just this utility now,
Yeah.
Like running water.
It's totally seamless.
Yeah.
But if you had tried to do that, say, 10 or 15 years ago, it would have been a very different experience.
Oh, absolutely. It would have been complete word salad.
Right.
The shrimp of happiness dances in the pot or something like that.
Exactly. But getting from that word salad to something that actually makes sense,
Yeah.
that's one of the oldest obsessions in computer science.
Really?
Yeah, we're talking about a problem that goes back to the late 1940s.
Yeah.
It's practically as old as the computer itself.
And that's what we're digging into today. The source material you pulled is this Comprehensive History of Machine Translation, or MT.
Mm.
And I think the goal here is to stop looking at that translate button as some kind of magic dictionary and start seeing it for what it really is, a code-breaking machine.
That is the perfect way to frame it. Because for the longest time, we were trying to teach computers to be linguists. We wanted them to understand grammar and syntax.
Right.
But the real breakthrough, the big one, happened when we stopped treating language like a humanity and started treating it like a math problem.
So let's go back to the beginning. You mentioned the 40s. I'm guessing this starts with the Cold War.
It does. The year is 1949, and there's a guy named Warren Weaver. Now, during World War II, computers were used to break enemy ciphers.
Like the Enigma code.
Exactly.
Yeah.
So Weaver looks at a document written in Russian, and he has this kind of wild idea. He says, when I look at an article in Russian, I say, this is really written in English, but it has been coded in some strange symbols.
Wait, hold on.
Yeah.
So he didn't think of Russian as a language. He thought of it as, what, encrypted English?
Basically, yes.
Yeah.
Sounds so naive now, but you have to remember the optimism of the time. I mean, they had just solved these massive ballistic calculations.
So they thought language was just another set of logical rules.
They figured, give us a few years, we'll punch some cards, and we'll solve translation.
And I'm guessing that did not happen.
Not even close. There was this famous demo in 1954 where IBM translated a few Russian sentences. It looked impressive on the surface, but it was basically a parlor trick.
How so?
They limited the vocabulary to only 250 words and used like 6 grammar rules. It was totally scripted.
But the government bought into it.
For a while, yeah. The U.S. poured millions into it. They were desperate to read Soviet intelligence. But by 1966, they realized they were just burning cash.
So what happened?
They commissioned this report, the ALPAC report, and it was devastating. It basically said, look, human translators are faster, they're cheaper, and they actually understand what they're reading.
Ouch. So the funding just dries up.
Completely. We entered what's now called the ALPAC winter. For about a decade, nobody in the U.S. wanted to touch machine translation. It was a career killer.
But obviously the problem didn't go away. So how did they try to dig themselves out of that hole?
Well, when the research finally picked back up in the 80s, mostly in Europe and Canada, they decided to get serious about linguistics. This is the era of rule-based machine translation.
Okay, so this is where they try to teach the computer the actual rules of the language, right?
Exactly.
Yeah.
And to understand how this works, the best way to think about it is something they call the Vauquot triangle. Or maybe a ladder is easier to picture.
A ladder. Okay, I'm picturing a ladder. What's at the bottom?
So the bottom rung is direct translation. This is just word-for-word replacement. I saw him becomes UOV in Portuguese. You're just swapping the tiles.
Which works for cat eats mouse, but completely fails for anything real.
Right. So you climb up to the next rung, transfer. Here, the computer actually analyzes the sentence structure. It looks at the English sentence, identifies the nouns, the verbs, the adjectives. It builds a kind of grammatical tree.
Okay.
Then it transfers that structure into the rules of the target language.
So it actually knows that in French, the adjective usually comes after the noun, whereas in English, it comes before. It's manipulating grammar.
Correct. But it is. There's the top rung, the holy grail. It's called interlingua.
I read about this in the notes. This is the idea that you don't translate from English to French. You translate English into meaning, like pure concepts.
That's the dream. You strip away the words entirely and convert the sentence into this language-neutral conceptual representation.
Wow.
And if you can get to that pure concept, you can then generate the output in any language you want. Japanese, German, Swahili, all from that one central source.
It sounds so elegant, like we just need a universal code for dog bites, man.
It is elegant. The problem is reality. Human language just doesn't map neatly onto universal concepts. Take a word like home.
Mm-hmm.
Does home mean the same thing to a nomad in Mongolia as it does to a stockbroker in New York?
Probably not. The cultural context is completely different.
And that's where interlinguage just breaks down. You end up having to write thousands and thousands of rules to define these concepts. It's incredibly expensive, incredibly fragile. You fix one rule, you break three others.
So these rule-based systems were just too rigid. They couldn't handle the messiness of the real world.
They worked for very specific, narrow things like weather reports. There was a system called Meteo in Canada that worked for 20 years.
Because weather reports are boring.
Exactly.
Yeah.
Cloudy with a chance of rain is easy, but for translating the entire internet, no way.
So this brings us to the big shift. We're in the 1990s now, the statistical revolution, and this is where that noisy channel concept comes in. When I read this, I actually had to pause because it seems so counterintuitive.
It is completely counterintuitive.
Yeah.
Researchers at IBM basically said, forget linguistics, forget grammar rules, let's just look at the data. They went right back to Warren Weaver's original idea of cryptography.
Okay, so explain the noisy channel model. The name makes me think of static on an old TV.
That's actually a great analogy. Imagine I'm trying to send you a message in English, but the wire is bad. It's noisy. By the time the message gets to you, the signal has been distorted. It's been scrambled. And weirdly, the scrambled output looks exactly like French.
So the computer pretends that a French sentence is just an English sentence that got corrupted by a bad signal.
Yes. And the computer's job is not to translate the French. Its job is to reconstruct the original English message that could have caused that French signal.
That seems so backwards. How does it even know where to start?
It uses probability. It relies on two giant pillars of data. The first is called the translation model.
Okay.
This represents faithfulness. It asks, does this French word tend to match this English word?
So it learns that maison usually pairs with house.
Right. It learns that by scanning millions of documents that have already been translated by humans, like UN proceedings. But if you only use that, you'd get that word salad we talked about.
Right.
You'd get the house blue is.
Because it's faithful to the French word order, but it's terrible, terrible English.
Exactly. And that's why you need the second pillar, the language model. This model doesn't care about the French at all.
Right.
It has only ever seen English text, terabytes of it, and its only job is to ask, is this a plausible English sentence?
So the translation model says, hey, maison matches house. And the language model says the house blue is garbage. The blue house is much more likely.
And the decoder is the engine that basically pits these two models against each other. It searches through billions of possible combinations to find the one sentence that is both faithful to the French and fluent in English.
This explains so much about those early Google Translate fails. The machine would sometimes pick a sentence that was perfect English, super fluent, but had nothing to do with the original meaning.
Yep.
Or it would give you the right words in a nonsensical order. It was just balancing those two probabilities and getting it wrong.
That's the trade-off. It's a game of pure statistics.
Let's look at a specific example from the source, because I think this really shows how the computer actually sees the text. The Greenwich example.
Okay, right. María no dio una bofetada a la bruja verde.
Which is, Mary did not slap the green witch. Now, in the old rule-based days, I would have assumed the computer knew that bruja verde was a noun phrase. But in statistical MT, it doesn't know what a noun is, does it?
No. It has no concept of nouns or verbs. It uses something called phrase-based translation, but phrase here just means a chunk of words.
A sequence of words.
It's just a sequence. So it looks at vía una bofetada.
Which means gave a slap.
In Spanish, that's 3 words. In English, it's 1. Slap. The computer doesn't know the grammar. It just looks at the alignment. It's like drawing lines between the English and Spanish sentences in the data. And it sees that every time dio una bofetada appears, the word slap tends to appear in the English version. So it learns to map that chunk of 3 words to that one word.
It's memorizing patterns, not learning rules.
Precisely. And it does the same for bruja verde. It learns that verde, which is green, usually flips its position when going into English. It's all just calculated probabilities based on millions of previous examples.
Okay, so we have this system that's churning out probabilities. But here's the logistical question. How do you grade it? If you're Google and you're updating your system every day, you can't have humans read millions of sentences to see if they're any better.
You definitely can't. It's way too slow and way too expensive. So they invented something called the BLEU score.
which stands for Bilingual Evaluation Understudy.
That's the one. It's basically a way to automate the grading. The computer produces a translation, then it compares its version to a reference translation, one done by a human, and it just counts how many chunks of words overlap.
So if the human wrote, "The cat sat on the mat," and the computer wrote, "The cat sat on the mat," it gets a perfect score.
Right. Perfect score.
But what if the human wrote, "The cat sat on the mat," and the computer wrote, "The kitty rested on the carpet"?
Then the computer gets a terrible score. A 0, probably.
But that's a great translation.
It is. And that is the huge flaw of the BLEU score. It measures word overlap, not meaning. It punishes creativity and synonyms.
So why use it?
Because it's fast. And if you run it over 1,000,000 sentences, it generally tells you if your whole system is getting better or worse, even if it's wrong on individual sentences.
It's a blunt instrument, but it works at scale. Okay, so statistical MT was king for a long time. But around 2014, everything changed again. We entered the neural era.
This is the paradigm shift. We moved from statistics to deep learning. Neural machine translation, or NMT.
This is what we're all using today. This is DeepL. This is modern Google Translate. What is the fundamental difference?
In the statistical method we just talked about, the computer chopped the sentence up into little bits. Pura verde de una bofetada. It solved the puzzle, piece by piece.
Right.
Neural networks don't do that. They digest the entire sentence at once.
The source material mentions vectors. Now, I know what a vector is in physics, but what is a vector in language?
Think of it like a digital fingerprint. The neural network takes the sentence, "the green witch," and converts it into a long string of numbers. That string of numbers, the vector, represents the meaning of that sentence in a massive multidimensional space.
So it's not looking up the word witch in a table. It's creating a numeric thought that represents witchness.
In a way, yes. And because it's all math, witch might be numerically close to wizard or magic in that number space. It captures relationships and nuance that simple statistics could never get.
But there was a problem with this at first, wasn't there? The long sentence problem.
A huge problem. Early neural networks had this bottleneck. They'd read the whole sentence, squish it down into this one vector, and then try to spit out the translation from that.
Okay.
But if the sentence was really long, like a paragraph from a legal document, the network would essentially forget the beginning of the sentence by the time it tried to translate the end.
It's like trying to memorize a whole paragraph instantly and then recite it backwards. You're going to drop stuff.
Exactly.
Oh.
And the solution to this, the big breakthrough, was a mechanism called attention.
Attention. I see this term everywhere in AI now. How does it work in translation?
Imagine a spotlight. Instead of trying to hold the whole sentence in its head at once, the attention mechanism lets the system shine a spotlight on specific words in the source sentence as it's generating the translation.
So if it's translating that French sentence about the house when it's about to write the word blue, it shines the spotlight back on the word blue in the original.
Yes. It creates a dynamic link. It says, for this next word I need to write, the most important part of the input is this word right here. It means the system can handle sentences of almost any length without losing the thread.
That feels so much more like how a human works. When I translate, I'm constantly looking back at the source text. I don't memorize it all at once.
And that's why the quality jumped so drastically around 2015, 2016. That's when you started seeing translations that felt shockingly fluent.
But, and there's always a but, we still haven't fired all the human translators. The source talks about post-editing.
No, we haven't. The industry has just shifted. Now, instead of translating from scratch, a human translator often takes the output of the neural network, which is maybe 90% good, and just polishes it. They fix the tone, they catch the cultural misses. It's become a hybrid workflow.
So it's like the machine builds the house and the human comes in to decorate it.
Or the machine builds the house and the human checks to make sure it didn't accidentally put the toilet in the kitchen. Because these neural networks can produce confident hallucinations.
Right.
They can create a sentence that sounds grammatically perfect, but is factually the exact opposite of the source.
And that brings us to the big question for me. We've gone from Warren Weaver thinking Russian was a code, to rule-based ladders, to statistical probability, to these massive neural brains using attention spotlights. The machines are incredibly good now, but do they understand what they're saying?
That is the black box problem. When a neural network translates a poem about love or grief, it can produce a beautiful moving output, but inside the system. It's just vectors. It's just math. It has no concept of what love actually feels like.
It's a really, really sophisticated parrot.
A parrot that has read the entire internet It can predict what word comes next with terrifying accuracy, but it doesn't have intent. It doesn't have a soul. It's manipulating symbols, not meaning.
Although I guess if the translation makes me cry, does it matter if the machine didn't feel it?
That is the question for the next decade.
Well, on that slightly existential note, I am going to go click translate on that Japanese cooking blog and just hope the machine isn't hallucinating the ingredients.
Just watch out for the shrimp of happiness.
Will do. Thanks for listening to this deep dive. We'll catch you on the next one.